and welcome to a quick video, this time on a tricky first order differential equation. This is like question 9 from paper M from Madasmaths. I'm guessing this is the one that Daniela was asking me to do, just because the first question on the paper, which is differential equations, looked quite routine, and I'm pretty sure it's this one. Okay, so this one, it's long. It's actually not too bad in some ways, but it is long, and it's got this annoying irreducible quadratic, two pairs of two irreducible quadratics, which you end up having to integrate. We'll see as we get into it. So first order differential equations, there's only really one new trick in further maths for solving first order differential equations outside of separation of variables, which you learn in the first A level. Well, when we've got something like this, I always think it's of that form, dy by dx plus py equals q. It's going to be basically integrating factor. That's what we're looking at here. Now, to solve this, we're going to have, but bear in mind that p and q are functions of x, yeah? Must be basically just strict functions of x. Only x is a variable, which is what you'd expect anyway. You're not going to have multivariable calculus. But, okay, we need it of that form. Have we got it of this form? Yes, we have. P being, of course, in this case, 1 over x, yeah? And the rule is you integrate P and then raise it to the power as a power of e, basically, and then multiply through by that. That is the integrating factor trick, isn't it? Put a little dx on the end there. So I'm going to have to, in this case, do e to the power of the integral of 1 over x dx, and that comes to e to the ln x, and that cancels really nicely to x, and you realise, I probably should have spotted this anyway, so I'm going to have to take my original equation, times it by x, and I get x dy by dx plus y equals 5x over this big, horrible product of two irreducible quadratics, as they're called. Right, like that. And now we can basically apply reverse product rule on the left-hand side. And that's what I mean by I should have really seen this coming, like you just got dy by dx of xy. I always find it very satisfying to quickly check this, because I find it much quicker going in that direction than that direction in terms of the thinking power. Differentiate that, you get 1, times it by that, you get y. Differentiate that, you get dy by dx, times it by that. Now, yeah, it's looking good. And so, oh, not yet. That obviously equals the right-hand side, which is the same old irreducible quadratic. Let me just write it down. It's annoying writing it down again and again, but you see where I'm going with this. And now I'm going to have to integrate the right hand side, yeah? And this is what I mean by this is painful. Now, when I saw this, initial thought was definitely this is partial fractions. You know, it looks like a partial fractions problem. Sorry about the appalling handwriting up there, but it's a +3. Okay, so this looks like a partial fractions problem, but you have to remember, look out for anything of the form x squared plus a constant, yeah? When that is a factor, then that is I call them type 4 partial fractions, like, because you go through type 1 to type 2 and type 3 in the A level, but it doesn't really matter what we call it. But the key thing is there's an irreducible quadratic, in other words a quadratic which, if you solved where it equals 0, well, you're going to get a complex number. That is the problem basically here. If it was x squared minus a number, then you can use difference of two squares to factorise it, you see. But if it's like this, you can't factorise it further, it's irreducible. And then this one's 4x squared plus 3. Well, you know, both of those are irreducible quadratics, so we're going to need to use partial fractions. Now, standard approach with partial fractions, when you've got something like some function of x over x, I don't know, let's make it interesting. Let's do something like this. Let's say you had a partial fraction to do like that. You'd have to do a over x plus b over x plus 1. And then you'd have to do like a cx plus d over the x squared plus 2. Yeah, that's the way you model that partial fractions problem. If you had, and you might have to do some other tricks as well. If you had, as x squared here, that would make it more awkward as well, and things like that. But anyway, I don't want to get too bogged down in partial fractions. The key thing is that in this situation, we're going to have to write it as, so, you know, this is almost worth just having like a little intermission you're working and just saying, consider, let the examiner know with just a brief word that you're just sort of breaking the argument. Consider 5x over x squared plus 2, 4x squared plus 3. It's like a little intermission in the middle of a long proof. Okay, that's going to be equal to, and in fact identical to, ax plus b over the first factor plus cx plus d over the second factor. Now when I look at this, I think, well, you can either try and do it in a really sort of like a showy way using I, which I might do at the end of the video if anybody's still watching, or you can actually just do it the boring way. 5x is identical to, it's going to be that times that times that, so we've got ax plus b times by 4x squared plus 3, and then cx plus d times by x squared plus 2. Okay, and we're just going to, multiply it all out and equate coefficients. So 5x is identical to, now what are you going to get here? Let's get it done correctly. This is the kind of point in the argument where I normally make a mistake. 4x cubed plus 4b x squared plus 3ax plus 3b. Same with the other one, cx cubed plus dx squared plus 2cx plus 2d, and then set up a big long system of equations. Okay, let's look at the x cubes. 4a plus c is 0. Let's look at the x squareds. 4b plus d is 0. Let's look at the x's. 3ax plus 2cx, well, that equals 5. Ooh, excitement. 3a plus 2c equals 5. And then the last one, 3b plus 2d equals 0. Okay, right, so what we could do is double, let's just solve both of these simultaneously. Double this one. 8b plus 2d is 0. Subtract 5b is 0. So b is 0. And you get d is 0. Boring, but it's done at least. Solving these, we get values. Okay, so if I double that, I get 8a plus 2c is 0. Subtract 5a is minus 5, so a is minus 1, and therefore c is 4. Okay, good. What have we discovered? We've discovered after that long, painful kind of process that xy is equal to the integral of, remind myself of the format again, it's going to be minus x over x squared plus 2 plus okay, what do we need here? Minus x over x squared plus 2 plus 4x over the other one. 4x squared plus 3 dx. Okay, we can now integrate these with Lunds. So, okay, why is it possible with Lunds? Well, if I stick a 2 there, and remember to times it by a half, I'll have a half minus a half ln x squared plus 2 plus, okay, that needs to be 8 really, doesn't it? So I'll stick a half out here and say that's a half, change that to an 8 ln 4x squared plus 3. I hope you can see what I'm doing there. It's a bit cheeky me doing that with I hope it's still technically accurate, isn't it? Plus c. Okay, right, and I've got this far, and I'm basically well on my way to solving this now. I've just got to plug in, as we always do here, half ln 7 over 6, x is 1. So y is a half ln 7 over 6 when x equals 1. That makes the left-hand side nice because I can just write half ln 7 over 6. And then I'm just plugging x equals 1 here, so I'm going to get minus a half ln 3 plus a half ln 7 plus c. Okay, let's double everything. Then we're going to get rid of those horrible halves. We'll just call it 2c for the moment. Minus ln 3 plus ln 7 plus 2c. Okay, so that's going to give me, when I simplify that, ln 7 over 3. Take it over here, I'm going to have ln 7 over 6 minus ln 7 over 3. Because that simplifies to ln 7 over 3 with log laws. And that actually cancels, because when you do 7 over 6 divided by 7 over 3, it's 7 over 6 times 3 over 7. So that's ln a half. It's 2c. And so c is a half ln a half. Lovely. Okay, we're really close now. We can just say, I wish I could actually see in this screen. I need to keep actually the answer with me just so I can see what it looks like. But we've got xy equals minus a half, and let's just take those halves out, ln x squared plus 2 plus ln 4x squared plus 3 and then we've got the c on the end. We'll see as a half. I've taken the half out, and so it's going to be, oh, well, let's not take the minus out either. Let's actually leave that in there. It might be slightly easier to see what we're doing with that in there. And then move the screen across a little bit, and so learn a half on the end. Okay, if we simplify, let's move this 2 over here, make it 2xy very quickly. You can see you're going to get ln of 4x squared plus 3 over, and now when you do that, you know, like do that one over that one, but then you're going to be adding ln a half, which means you're going to be times at the top by 1 and the bottom by 2. And so you're going to get 2x squared plus 4, which I think is what they've got, and then this leads to the final answer, 1 over 2x ln 4x squared plus 3 over 2x squared plus 4. Is that right? I think that's right. Yeah, cool. And that's it, basically. That's all you need to do. Yeah, maybe I'll show you the you know, sort of like ridiculous way of doing the partial fractions some other time. I'm quite tired. Okay, bye-bye.